Hello, I am Madeline Loveday, and this is a comparative analysis of high-entropy ceramics prepared via steric entrapment and solid-state synthesis methods. We are looking into structure, particle size, and homogeneity. I'm going to zoom in on each section so that we can follow a little easier. This project was designed to compare solid-state synthesis and steric entrapment methods, looking into crystal structure using X-ray diffraction, particle size using scanning electron microscopy, and homogeneity using electron probe microanalysis. Ceramic oxides were prepared using the two synthesis methods. This project has an emphasis on high-entropy materials. High-entropy materials have 5 or more elements in equimolar amounts, which increases the configurational entropy and favors the formation of a single phase. High-entropy materials have improved functional properties called the cocktail effect, which low-entropy oxides lack. The solid-state synthesis reaction involves mixing raw materials and heating them in a furnace to promote diffusion via high temperatures. Ultimately, this method is inadequate as powder mixing is imperfect and diffusion through heat treatment is inefficient. The steric entrapment method mitigates these issues. This method consists of homogeneously dissolving the cations in water and adding a solution of long polymer chains of PVA, which traps the cations and prevents segregation and precipitation. The solution can then be dried and calcined to burn off the polymer and produce a uniform single-phase oxide powder. The single-phase powders created through steric entrapment will be used to grow high optical quality crystals using the micro-pulling down method. The following compositions used in the experiment are a high-entropy sesquioxide with cerium, praseodymium, europium, terbium, and yttrium, a high-entropy perovskite with the same cations, and a low-entropy yttrium aluminum garnet. A summary of both methods is shown in these flowcharts. The solid-state synthesis method requires the raw materials to be weighed in equiatomic amounts, and these raw materials to be mixed in a ball mill mixer and then pressed into a pellet and centered at 1500 degrees Celsius for 10 hours. The steric entrapment synthesis method requires nitrate salts to be weighed in equiatomic amounts and then dissolved in DI water. PVA is then dissolved in DI water and combined with the dissolved nitrate salts. This combination is then heated until the water is evaporated, which forms a sort of foam. This foam is then dried in a furnace in a fume hood at 200 degrees Celsius and then ground into a powder and calcined in a furnace in a fume hood at 550 degrees Celsius. This is then ground again and pressed into a pellet and then crystallized in a furnace at 900 degrees Celsius for an hour. All of these samples were ground manually with a mortar and pestle and then characterized in the powder form. Here are the SEM results. For the high-entropy sesquioxide, you can see that the solid-state synthesis method created larger particles than the steric entrapment synthesis method did. For the high-entropy perovskite, the solid-state synthesis method also created larger particles than steric entrapment did. For the low-entropy garnet, solid-state created smaller particles than steric entrapment did. As the SEM images show, for the high-entropy oxides, steric entrapment synthesis results in smaller particles, but for YAG, the solid-state synthesis method created smaller particles than steric entrapment did. Here are my X-ray diffraction results. For the high-entropy sesquioxide, you can see that both methods created a single phase, while the steric entrapment synthesis method created the single fluorite phase. The solid-state synthesis method created the single bixbyite phase. For the high-entropy perovskite, neither of the methods created a single phase, and both methods created a mix of the perovskite and garnet phases. Also, as you can see, with the steric entrapment synthesis method, sample was centered at 1100 degrees Celsius. This is because when the sample was centered at 900 degrees Celsius, it did not entirely crystallize and needed to be heated at a higher temperature. For the low-entropy garnet, the steric entrapment synthesis method created the single garnet phase, while the solid-state synthesis method created a mix of the perovskite and garnet phases. Here I have images of the crystal structures that my materials formed, if you're curious. Here I have my EPMA results showing that for the high entropy sesquioxide, the steric entrapment synthesis method, which is in the blue bars, is closer to the nominal composition for the rare earth elements. And for my high entropy perovskite, the steric entrapment synthesis method also was closer to the nominal composition of the rare earths. But for aluminum, the solid-state synthesis method is closer to the nominal composition. For the low-entropy garnet, the steric entrapment synthesis method created materials that were closer to the nominal composition of both yttrium and aluminum. Overall, we learned that the steric entrapment synthesis method more reliably produces single-phase ceramics. Also, for all compositions, steric entrapment synthesis method produced more homogeneous samples that were closer to the nominal expected values for percent composition. The solid-state method requires a longer sintering time and higher temperatures, and it fails in producing single-phase ceramics for some compositions such as the yttrium aluminum garnet. We also learned that both methods can form different crystal structures for the same composition. Because steric entrapment is more reliable and produces higher quality samples, it is therefore the more effective method, though it needs to be refined for high entropy oxides. This research will be used to inform future precursor synthesis parameters in future crystal growth via the micro-pulling down method. This project is part of a larger project at the Scintillation Materials Research Center. This research contributes to the protection of medical imaging instruments. This project is supported by the National Science Foundation. I would like to thank the Center for Materials Processing for partial funding. I would also like to thank Dr. Michael Kaler at GIAM for his assistance with X-ray diffraction, Dr. John Dunlap and Dr. Chris Wetland for their assistance with SEM, and Dr. Alan Patchen for his assistance with EPMA. Thank you.